Dear students, I welcome you for the today's lecture related to the frequency response technique, in which we are going to study the details related to the Bode diagram. How to plot a Bode diagram, that we are going to discuss today. Basically, it's a stability for a control system. For that, different methods are there. One is your Routh-Harry test, root locus diagram, and this is the third, the frequency response technique. Basically, frequency, when it is there, then there is some variations that will be arising. So in general case, it is our sinusoidal input, that is the forcing function, which is considered to be as the frequency input for our frequency analysis. So response of control system to the sinusoidal input at various frequencies. This is why it is important to study the frequency response, because our sinusoidal inputs are very common in our chemical process industries. Every time you can observe the fluctuations in the response. So whatever the input is there, the response of the control system to the sinusoidal input at various frequencies. So this frequency response analysis determines the output sinusoidal wave when a linear system is subjected to the sinusoidal input. And its frequency response is, we have to analyze its characteristics. How that is to be plotted, that we are going to study. It's basically a graphical method, and it talks about the stability, the different optimum values of the k, that is your controller gain, the integral time, and the derivative time. So this is our frequency response technique. However, we have already studied the forcing function, in which we have calculated the response, that is yt, which is equal to a omega tau upon 1 plus omega tau square e raised to minus g upon tau plus a upon under root of 1 plus omega tau square plus into sine of omega t plus theta. At steady state, you get this equation and the amplitude ratio, which is 1 upon under root of 1 plus omega tau square. This is for the first order system. That is 1 upon, for a transfer function, 1 upon 1 plus tau s. So you are getting the amplitude ratio as 1 upon under root of 1 plus omega tau square. Now in this frequency response technique, it is slightly somewhat different. We have to convert the system into the complex number. That is the transfer function for the first order system, that is 1 upon 1 plus tau s or k upon 1 plus tau s, and substituting s, that is equal to the j omega. That means we are converting this system into the complex number by substituting s, which is equal to j omega. So to rationalize this, we multiply the numerator and denominator by 1 minus j omega tau, and separating the real part, that is k upon 1 plus omega square tau square, and the imaginary part, that is incorporating the j. So j, that incorporates the imaginary part. So for this, we will substitute this as k upon 1 plus omega square tau square, which is equal to m, and k omega tau upon 1 plus omega square tau square as n. So substituting this real part, which is equal to m, and imaginary part, which is equal to the n. Now if we will plot on this complex number line, so that the imaginary part, imaginary axis is your y axis. So this is the n part, which is represented as omega tau upon 1 plus omega tau square, and the real axis that is indicating the 1 upon 1 plus omega tau square, which is m. Now this is the AB is your imaginary part and OB is your real part, real axis part. So OA, that is your hypotenuse, and theta is the angle made by OA and OB. So OA, that will be nothing but the under root of AB square plus OB square. Now AB square is your imaginary part square upon OB, that is your real part square. So this OA, that becomes equals to the under root of m square plus n square, which is nothing but under root of real part square plus imaginary part square. Now we have already calculated the real part and the imaginary part. Substitute these two values, OA, which is equal to under root of real part, that is 1 upon 1 plus omega tau square whole square, plus imaginary part, that is minus omega tau upon 1 plus omega tau square sub whole square. So OA, that comes as under root of 1 plus omega tau square. This is nothing but the amplitude ratio. This is the amplitude ratio, which is equal to the under root of 1 upon 1 plus omega tau square. So our first order system Gs, which is equal to Ys upon Xs, which is equal to 1 upon 1 plus tau s, and its amplitude ratio will become equals to 1 upon 1 plus omega tau square. You have to remember that for this transfer function 1 upon 1 plus tau s, the amplitude ratio comes as 1 upon 1 plus omega tau square, because we are directly using the similar transfer function and calculating the amplitude ratio directly when we will solve the numericals. That is why I am asking you to remember this. Instead of doing all these things, that is writing it in terms of the complex number, then rationalizing, then simplifying to calculate the imaginary axis and the real axis. Finally, you will get the amplitude ratio as under root of 1 upon 1 plus omega tau square. That is why it is easy to convert your transfer function directly into the amplitude ratio. So whatever the tau value, say 0.1 tau if it is there, so it becomes 0.1 omega square. If it is 3, then it will become 3 tau square, 3 omega square. So it is like that. Tau will be as it is and s will be replaced by omega. Now the phase angle. The phase angle, that is, it can be calculated as your perpendicular upon the hypotenuse. So base upon perpendicular upon the base. So theta, which is equal to the n upon m, that is writing the imaginary part upon the real part. So theta, that comes as the tan inverse of minus omega tau. This is imaginary part upon real part. So again we will remember that for a transfer function of 1 upon 1 plus tau s, theta, which is equal to tan inverse of minus omega tau. So tau will be there. If the transfer function is 1 upon 1 plus 2s, then it will be tan inverse of minus omega 2. Now actually how to plot a Bode diagram. This is what the initial part where we are calculating the amplitude ratio and the phase angle. After the calculation of amplitude ratio and phase angle, actually the Bode plot that is obtained. As the Bode plot consists of plots, that is, one is the variation of logarithm of amplitude ratio with the radian frequency, and second, the variation of the phase angle with radian frequency. That is what we have written these two equations, that is, one is the amplitude ratio and second is the phase angle. Now this amplitude ratio, how it varies with the omega, that is our radian frequency, and this phase angle, that is going to vary with this radian frequency. So these two equations, they are very important to plot a Bode diagram. Now we will see this Bode diagram, that is what the amplitude ratio, that is on the y-axis, and the radian frequency, that is on the x-axis. So it's a plot of amplitude ratio versus omega t on the log graph paper. Now you can see the values on this graph paper, that is 1, 0.1, 0.01, 0.001, and so on it will be. And on the upper side, 1, 10, 100, 1000, it will be like that. So similarly on the x-axis also, it is the value is 1. Then on the right hand side, it's 10, 100, 1000, 10,000, and so on. However, on the less than 1, that is 0.1, 0.01, 0.001. So how you are plotting this is very important. So first we have to understand the log graph paper, and then we are directly putting the values of amplitude ratio on this log graph paper. So amplitude ratio against the omega tau, that is there, we are directly plotting amplitude ratio on the y-axis and omega tau on the x-axis. So how the numbering are there in case of your log graph paper, that is very much essential. Then second plot, that is related to the phase angle against the omega tau. Phase angle against the omega tau. That is what our second relationship, phase angle theta, which is equal to tan inverse of minus omega tau. So this is what the second graph, that is the phase angle against omega tau, this is plotted. Again, that is on the x-axis, omega tau, that is on the log graph paper, and the phase angle, they are 0, minus 45, 90. Then on the upper side it is plus 45, 90, 135, 180. It will be like that. So omega, that is on the log scale. Amplitude ratio, that is also on the log scale. Now how to plot this amplitude ratio? So amplitude ratio, you can see here there are two lines. One is the LFA and second is the HFA. LFA is low frequency asymptote. Low frequency asymptote is LFA, and high frequency asymptote, that is HFA. So you have to draw the two lines, that is, one is low frequency asymptote and second is the high frequency asymptote. And the point of intersection of these two lines, that will be called as the corner frequency omega dash. That will be called as corner frequency omega dash. The point of intersection of low frequency asymptote with the high frequency asymptote. Now how to plot this low frequency asymptote and the high frequency asymptote lines? So basically it is the equation of your amplitude ratio, that is what is needed. So amplitude ratio, which is nothing but under root of 1 upon 1 plus omega tau square. Now low frequency asymptote, when we are defining, that means omega tends to 0. It is not actually 0, it tends to 0. That means it will have a very low values. That means it will have a very low values. It is not actually 0. There is a difference between the actual 0 and the values tending towards the 0. That is why we are plotting here. It tends to 0. That means 1, 0 0.1, 0 0.01, 0 0.001 and so on. That means it is tending towards 0. That is not actually 0. So next subsequent will be 0.0001. After that 0.4 times 01. It will be like that. It is not 0. It is tending towards 0. So low frequency asymptote W omega, that is tending to 0. That means omega tau will have a very small value. So when you substitute this very small value here in this equation, so 1, it will be same as 1. 1 plus a very small value of omega tau. And again that of square. So it will be nearly almost equal to the value of 1. So 1 upon 1 under root, that will be 1. So that is what the amplitude ratio, that comes as the 1. Then the log of amplitude ratio, if you will take the log for 1, that comes as the 0. So as the amplitude ratio is 1, when it is plotted on the logarithm plot, it becomes a straight line. So it's a straight line passing through 1. Amplitude ratio of a value 1. It becomes your low frequency asymptote. That is what y is equal to mx plus c. Y is your amplitude ratio and x is your omega. So amplitude ratio, which is equal to the 1. Then next is the high frequency asymptote. This is for the higher values of omega. Higher values of the omega, that means it is 10, 100, 1000, 10,000, 1 lakh and so on. So the values becomes on the higher side. Now if we will substitute this value of omega tau, which is tending towards infinity, that means I am tending towards infinity, I am adding 1, so it becomes a negligible value. And that is why amplitude ratio I can write as 1 upon omega tau whole square. When I will take the under root of it, it becomes 1 upon omega tau. So that is why amplitude ratio, which I am writing as 1 upon omega tau. Now taking log of this amplitude ratio, which is equal to log of minus omega tau. Now when this is plotted, y is equal to mx plus c. Y is nothing but your amplitude ratio and it is plotted against omega tau. So this will have a slope of minus 1 when it is plotted on the log graph paper. And that is why we are putting the negative slope of minus 1. That means a negative slope. Slope of minus 1. This is your negative slope. If it would have been a positive slope, then the line would have been in this direction. And when it is a negative slope, the line is in the negative direction and its slope is minus 1. That means your gradient is on the y-axis is same as that of the gradient on the x-axis. If you will see here, the gradient on the x-axis, that is 0.01 and gradient on the y-axis, that is 0.01. So you can consider this as the gradient, and that is why the x is same as y. That is why the slope is -1 for this line. Understanding these lines of low frequency asymptote and high frequency asymptote is very much important in plotting this Bode plot. So amplitude ratio, it requires the two things. One is the low frequency asymptote, second is the high frequency asymptote. So this low frequency asymptote, that is obtained by plotting or substituting the value of omega tends to 0, and that means omega tau tends to 0. That means amplitude ratio will be equals to 1. Then the log of amplitude ratio, that becomes equals to 0. So if you will plot the amplitude ratio, it becomes a straight line, that is your low frequency asymptote. Then high frequency asymptote, omega tends to infinity. That means omega tau tends to infinity. That is why 1 upon omega tau will be equals to the amplitude ratio. So log of amplitude ratio, that becomes equal to minus log of omega tau. Now if we will plot a graph, so amplitude ratio, which is equal to 1 upon my omega tau. Now this is log of amplitude ratio y, and the mx, x is omega tau, slope is -1. So here the slope comes as the -1. Here this is your y value, this is your x value, and the slope, that becomes equals to your -1. So slope is your -1. When it is plotted on the logarithmic plot, the line is with a slope of -1. So this is a line of slope with a -1. Now the point of intersection of low frequency asymptote and high frequency asymptote is known as a corner frequency omega dash, and which is 1 upon tau, that is omega tau, which is equal to 1 upon tau. So the sketch of variation of amplitude ratio versus omega can be obtained by plotting approximate asymptotic behavior for omega tends to 0 and omega tends to infinity, passing through the point of amplitude ratio, which is equals to 1. Passing through the amplitude ratio, which is equals to the 1, and having the corner frequency of 1 upon omega dash, which is equal to 1 upon tau. Now next is a phase angle. Phase angle theta, which is equal to the tan inverse of minus omega tau. Theta, that is equal to tan inverse of minus omega tau. Now as we have substituted the two different values, here also we are going to calculate the different values of omega tau, and substituting the different values of omega tau and calculating the value of phase angle theta. So for omega tends to 0, then next is omega equals to 1, and the third is omega tends to infinity. That three things we will be requiring to plot on this graph. omega tends to 0, omega equals to 1, and omega tends to infinity. That is what omega tends to 0, omega tends to infinity. This is what the omega tau is there on the x-axis, and on the y-axis it's a phase angle theta that will be there, and this is the origin 1. This is the point at which 1 is there, omega tau. So omega tau, now if I will substitute, tends to 0. So what happens to tan inverse of 0? Tan inverse of 0, that becomes equals to the 0. So phase angle is 0. Then I will substitute omega tau, which is equal to 0.01, and will calculate the value of phase angle by substituting tan inverse of 0.01. So theta, that will be calculated as minus 0.572. So this is my minus 0.572. Then value of 0.1, instead of 0.1, I will now calculate the value for 0.1 and will calculate the phase angle. So it comes as minus 5.71. So this is my value of minus 0.571. So this line actually drops like this. So this can be considered as your 0.57 value, as it is 0.45. Then omega tau, which is equal to 1, the calculated values of phase angle is 45. So you will get this value for omega tau, which is equal to the 1. Then substitute it equals to the 10. Omega tau equals to the 10. Substitute this value, calculate the value of theta, so that you will get theta as 84.28. So for this value of 10, the value of minus 84.28 is there. So this value will correspond to this numerical value. Then towards the 100, yes, omega value that tends to 100. So phase angle, that comes as 89.42. Now here its the value is 89.42. Now if I will substitute the value of 1000, okay, omega tau, substitute it as a infinity, the phase angle that comes as minus 90 only. So when you travel from 100 to the infinity, there is only difference of 0.6. 0.6. So this is 89.42 and this is 90. You will travel from 100 to infinity. So irrespective of putting the or continuing the further values, I am restricting my graph towards 100 only, so that it approximately reaches to the 90, which is my final destination value, towards the infinity. And this is how you are going to plot a phase angle. So you will require to plot the two graphs, that is the amplitude ratio versus the frequency, and the phase angle against the frequency. Now this is for what we have done it for the first order system. Now we will do it for the second order system. Our second order transfer function is nothing but 1 upon tau square s square plus 2 phi tau s plus 1. Then substituting s, which is equal to the j omega, and writing this s as j omega, s as j omega. So you will get this equation. Then this can be simplified here as j square, which is equal to the minus 1, j square, which is equal to the minus 1. So this is what t square omega square will become a negative sign. So this is what t square omega square is provided with a negative sign. So g of j omega in terms of a complex number, then we are going to rationalize it and separating the imaginary part, separating the real part and the imaginary part. So this is what the j imaginary part is there. Then amplitude ratio is nothing but the under root of imaginary part square plus the real part square. So this, after simplification, you will get the amplitude ratio, which is equal to 1 upon under root of 1 minus tau square s square whole square plus 2 phi tau omega square. And the phase angle theta, that comes as the imaginary part tan inverse of imaginary part upon the real part. So this is the imaginary part, the same imaginary part, and the real part that will be there. Okay, 1 minus tau square omega square whole square plus 2 phi tau omega square, that will get cancelled. So this is your real part square plus imaginary part square. After simplification, amplitude ratio, that comes as 1 upon 1 minus omega tau square whole square plus 2 phi omega tau. And theta, that comes as tan inverse of minus 2 phi omega tau upon 1 minus omega tau whole square. Now plotting a Bode plot. For that, we require the low frequency asymptote and the high frequency asymptote. So the low frequency asymptote is obtained by substituting the omega tau tends to 0. So omega tau tends to 0, the amplitude ratio, that comes as the 1, and the transfer function of a proportional controller, that is proportional controller, we will see. So GC, which is equal to the KC, is our transfer function. Now writing this in terms of the complex number, G of JW, which is again equals to the KC. Now here it's a purely a real number, that is KC is there, no imaginary part. So imaginary part is 0, and that is why the amplitude ratio, which is equal to the under root of KC square, which is nothing but the KC. So amplitude ratio upon KC, which is equals to the 1, and in case of a phase angle, theta, which is equal to tan inverse of imaginary part upon real part, which is equal to tan inverse of infinity, which is nothing but the 0. So first we will plot the imaginary amplitude ratio upon Kc. So amplitude ratio upon Kc, which is equal to the 1. So it's the amplitude ratio upon Kc against the omega, that will be a straight line passing through the 1. And what happens to the phase angle? that comes to the 0 for imaginary part upon real part, and there is no value of omega which is going to vary. So irrespective of the variation of the omega value, the phase angle that comes as the 0. So it's a straight line for a proportional controller. This is a plot, Bode plot for a proportional controller. It gives you a straight line. A simple question that can be asked. The amplitude ratio for the Bode plot with the proportional controller. Is it a straight line with a negative slope, with a positive slope, or with a negative and positive slope? So it's a negative, it's a straight line, slope of 1 only. Now next is the transfer function of a PD controller. So for a PD controller, the transfer function is Kc into bracket 1 plus tau ds. Then transformation obtained by substituting s, which is equal to j omega, that is converting it into the complex function. So s that becomes equals to the j omega. So 1 plus j omega into tau d, which is equal to Kc into plus Kc into j omega into tau d. So a real part and the imaginary part that will be there. So real part square Kc square and imaginary part, that is Kc omega tau d whole square, and imaginary part upon the real part theta. Theta that is equal to tan inverse of imaginary part upon real part. So plotting the low frequency asymptote and the high frequency asymptote. So low frequency asymptote LFA, which is omega tends to 0. So omega tau d value that tends to the 0. That is why amplitude ratio upon Kc that is equals to the 1. So log of amplitude ratio upon Kc that is 0. So it is a straight line. So low frequency asymptote is a straight line with 1 as its value. There is no slope. Then the high frequency asymptote, omega tends to infinity. So amplitude ratio upon Kc, which is equal to omega tau d, substituting omega with a higher values. So amplitude ratio upon Kc, which is equal to the omega tau d. So log of this will be is equal to the log of omega tau d. So y is equal to mx plus c. Y is log of AR upon Kc and log of omega tau d. So that is what we have plotted on the omega tau d on the x-axis. So the slope will be is equal to plus 1. So it's a line passing through the AR upon Kc, which is equal to 1, and tau d, omega tau d, which is equal to the 1. So it's a slope of plus 1. Then next is the phase angle, plotting a phase angle. So phase angle for this, that is tan inverse of omega tau d. Now tan inverse of omega tau d, that is nothing but theta, which is equal to tan inverse of omega tau d, which is equal to, I am going to substitute the different values for omega tau d. इसकी जो कुछ वैल्यूज है, ये एक तो पहले 0 सब्स्टिट्यूट करने की है, देन 1 सब्स्टिट्यूट करने का है, एंड देन इंफिनिटी सब्स्टिट्यूट करने का है. And in intermittent values also you can substitute to get a good graph. So tau d, omega tau d, when I am substituted here as 0, the phase angle that is becomes 0. Then for 1 omega tau d is equal to 1, the phase angle that comes as the minus 45. Sorry, it is plus 45 only. Then when I will calculate omega tau d, which is equal to 10, the phase angle is plus 84.2. Then for 100, the phase angle is 89.4, and for infinity, the phase angle is plus 90. So this is a graph that is consisting of the theta, phase angle, and omega tau d values. So for 100 values, that comes as 89.4. That means here you have reached to the 89.4 numerical value. The next is PI controller. So the transfer function for PI controller GS, which is equal to Kc into bracket 1 plus 1 upon tau is. Converting into the complex plane, substitute S is equal to j omega, substituting S which is equal to j omega, simplifying it, separating the real part, and the imaginary part. So real part square plus the imaginary part square. So you will simplify into this thing. And similarly, the phase angle theta, which is equal to tan inverse of imaginary part upon the real part, it simplifies to 1 upon minus 1 upon omega tau I. Now next is plotting a graph for this. The low frequency asymptote, that is omega tends to 0 or omega tau I tends to 0. So amplitude ratio upon Kc, which is equal to 1 upon omega tau I. That is what? Amplitude ratio, which is equal to under root of 1 plus 1 upon omega tau I square. So it will have the value of 1 upon omega tau I. So log of amplitude ratio upon Kc, which is equal to minus log of omega tau I. So this is a line passing through amplitude ratio of AR upon Kc, which is equal to 1, omega tau I, which is equal to 1, and having a slope of minus 1. So it's a slope of minus 1 line that is to be plotted. Then the high frequency asymptote, omega tends to infinity, substituting the omega value here under root of 1 plus 1 upon omega tau I whole square. So amplitude ratio upon Kc, which is equal to 1. So log of amplitude ratio upon Kc, which is equal to 0. The point of intersection of low frequency asymptote and high frequency asymptote, that is known as corner frequency, and which comes as the tau I, which is equal to 1 upon tau I. The next is the phase angle theta, which is equal to minus tan inverse of 1 upon omega tau I. So substituting the value of omega tau I, which is equal to 0, 1 or infinity. Also we can substitute the intermittent values also. So 0, you will get the phase angle as minus 90. For 1, is the phase angle is minus 45, and for infinity the phase angle is 0. So when you will plot for 1 omega tau, which is equal to 1, the phase angle is minus 45. This is what? The phase angle is minus 45. For 0, the phase angle is 90. So here for 0, or you can say for the small values, the phase angle tends to 0, and for the higher values, the phase angle tends to minus 90 here. So this is for 0, the phase angle is minus 90. Now next is the transfer function for PID controller.